A GPU with 16.96 teraflops of raw computing power should have beaten anything you put in front of it without trying. But it lost to a machine running at only 1.969 teraflops. Not a close loss, not a photo finish. The weaker machine finished the job almost 149 times faster, using barely a ninth of the power the GPU had sitting on the table. That number comes from a peer-reviewed paper, and once you understand what happened inside that test, you will see why chipmakers betting everything on bigger processors should be worried. Because here is the headline you probably saw. China built a faster AI chip than Nvidia. That headline is wrong, and the way it is wrong matters more than the number itself. A team at Peking University did not build a faster chip. They did not out-engineer Nvidia's silicon, and they are not claiming to. What they built was a way to stop chips from waiting on each other. And it turns out that waiting, not raw processing power, is the actual bottleneck strangling modern AI hardware. Fix the waiting, and a machine with a fraction of the horsepower can leave a full-size GPU in the dust. Stick around, because the mechanism behind this is stranger and more important than a spec sheet number. Now, to understand why this result is even possible, you have to understand what is actually happening inside a modern AI chip while it runs. Picture a factory floor with the fastest workers in the world standing at their stations. That is your GPU, thousands of processing cores, each one capable of finishing its task in a fraction of a second. But every single one of those workers is connected to a warehouse down a long, narrow hallway. Every time a worker needs a new part, they have to send someone down that hallway, wait for them to find it, and wait for them to bring it back. The workers are not the problem. The hallway is. Engineers call this the memory wall, and it has quietly become the defining constraint of the entire AI industry. A processor core can chew through calculations in nanoseconds. But the data that core needs, the weights, the activations, the intermediate results, all of it has to travel over copper wires between the chip and its memory, and between one chip and the next chip in the cluster. Copper has limits. It heats up under sustained load. It loses signal strength the farther it travels. And every AI cluster running today, from data centers in Virginia to server farms outside Beijing, has cores burning through their workload in milliseconds and then sitting idle for the rest of the cycle, waiting for data to catch up. To put that in perspective, the theoretical top speed printed on a GPU's spec sheet and the speed it actually sustains while running real workloads are two very different numbers, precisely because so much of that runtime gets lost to memory access instead of actual computing. This is not some secret buried in a research paper. It is just really, really hard to fix, because the fix means rethinking how chips talk to each other, not just making the chips themselves faster. You can build the fastest worker in the world. If the hallway to the warehouse stays the same width, the factory floor still only moves as fast as that hallway allows. And that idle time is not just a technical footnote. It is a business problem hiding inside every AI company's budget. A GPU cluster is one of the most expensive pieces of infrastructure a company can buy. And every hour a chip spends stalled on a memory request is an hour of that purchase price generating nothing. Multiply that across a data center running thousands of chips around the clock, and the memory wall stops being an engineering curiosity and starts being one of the largest hidden costs in the entire AI industry. Solve it, even partially, and you are not just making chips faster. You are making every dollar already spent on hardware go further. This is the problem the Peking University team decided to attack. The corresponding authors on the paper, Xu Haowen and Wang Xingjun, led a group that published their results in the peer-reviewed journal National Science Review. And their answer to the memory wall was almost stubbornly simple. If copper wires are the hallway causing the bottleneck, stop using copper. Use light instead. It helps to understand what an FPGA actually is here, Because the choice matters. A GPU is a fixed chip, built once and optimized specifically for the kind of math AI models need. An FPGA, short for Field Programmable Gate Array, is a chip you can rewire after it leaves the factory, reconfiguring its internal circuits for whatever task you pointed at. FPGAs are common in prototyping exactly because of that flexibility, and they are not, by design, built to match a GPU's raw throughput on AI-style math. Choosing 5 FPGA chips instead of a single high-end GPU was not an attempt to build the fastest individual processor. It was a deliberate choice to prove the interconnect itself, the light-based connection between chips, could carry a system past a machine with far more raw compute sitting inside a single package. Light does not carry the same baggage electricity does. It does not generate resistance heat over distance. It does not lose meaningful signal strength across the short runs found inside a server rack. Physicists have known this for decades, which is exactly why fiber optic cable replaced copper for long-distance internet backbones a generation ago. The idea of doing the same thing inside a computer, chip to chip, is not new either. What has been missing is a way to build that light-based connection cheaply enough and reliably enough to actually put it inside working hardware instead of a physics lab demonstration. Here is what the team actually built: 5 FPGA chips, which are reprogrammable processors used widely in prototyping and specialized computing. Each one fitted with a custom silicon photonic transceiver capable of running at 400 gigabits per second. Instead of copper traces carrying electrical signals between chips, these transceivers convert electronic data into pulses of light and send it down optical pathways to wherever it needs to go next. And connecting all 5 chips together sits a 16 by 16 non-blocking optical switch built on a silicon-on-silicon platform, the same general manufacturing approach used to make ordinary computer chips, just applied here to guiding photons instead of electrons. That switch is the real engineering feat buried in this paper, and it is easy to miss if you only skim the abstract. It achieved a total loss of no more than 5 decibels across a nearly 100 nanometer band centered at 1,300 nanometers. In plain terms, when light enters that switch and gets routed to wherever it needs to go, almost none of the signal degrades along the way. Optical switches have existed in labs for decades. Getting one this clean, this low loss, across that wide a wavelength band, and non-blocking, meaning any input can reach any output without a traffic jam forming behind it, is the part that made the rest of the system actually usable instead of theoretical. So picture the factory floor again, but now the hallway between every worker in the warehouse has been replaced with a beam of light. No physical wire heating up under load. No electrical resistance eating into the signal the farther it travels. Data moves between chips at close to the speed of light through that medium, and the switch makes sure it always arrives at the correct station without a queue forming behind it. The FPGA chips in this test were never the fast part, and they were never meant to be. Each one individually is modest hardware. The light connecting them is what changed the outcome. This is not the first time an industry has hit a wall made of copper and solved it with light. Telecom companies ran into almost the identical problem decades ago, when copper telephone lines could not carry the volume of data the internet needed. Fiber optic cable did not make any single computer faster. It removed the bottleneck sitting between computers, and that removal is what actually unlocked the internet's growth. The Peking University team is applying the same fix at a much smaller physical scale, chip to chip instead of city to city, but the underlying logic is identical. You do not always need a faster engine. Sometimes you need a wider road. This is also why the comparison to a single commercial GPU looks so lopsided on paper. A modern GPU packs enormous raw compute into one chip, but that compute still has to reach across copper to talk to memory and to other chips in a cluster. The Peking University system spread its workload across 5 much weaker chips, but gave those 5 chips a connection to each other that barely loses any time or signal at all. The system was not competing on horsepower. It was competing on how much of that horsepower actually got used instead of sitting idle, waiting on a hallway. To put the actual numbers in perspective for a second, the system used just 0.116 of the total computational capacity of a single commercial GPU to do the job, roughly 1/9 of what that GPU had available, and still finished the task almost 149 times faster. If you tried to explain that gap using compute power alone, it would not make sense. 9 times less horsepower should never translate into that much more speed. The only way that math works is if the GPU being compared against was spending the overwhelming majority of its time not computing at all, just waiting on data that had not arrived yet. The photonic system was not winning a horsepower contest. It exposed how much of a modern GPU's rated performance never actually gets used in practice, because the chip is idle far more often than the spec sheet on the box would ever suggest. And the system does not stop at 5 chips. The switch architecture the team built can scale up to 16 interconnected processing chips, with an aggregate switching bandwidth reaching 6.4 terabits per second. The 5-chip test that produced the 149 times result was, by the researchers' own design, the small-scale proof. The architecture underneath it was built with headroom well beyond what was actually tested, which is a meaningfully different claim than a one-off lab trick that tops out at the exact configuration shown in the paper. There is a physical side effect worth sitting with too. Copper interconnects do not just slow data down, they generate heat while they do it, and heat is one of the largest ongoing costs of running a modern AI data center. Every rack needs cooling infrastructure built specifically to pull that heat away from the chips before it damages them. An optical interconnect that loses almost none of its signal generates far less of that wasted heat in the first place. That is not a detail buried in the paper's abstract, but it is the kind of downstream consequence that makes chip-to-chip photonics worth billions of dollars in research funding across multiple countries, not just China. Intel, MIT, and several other institutions have published their own silicon photonics research over the past decade, chasing the same basic prize, a data center that spends less energy fighting its own wiring. If you are finding this breakdown useful, subscribe. This channel covers the technologies coming out of China that most Western coverage either misses entirely or gets wrong in the retelling, and there is a lot more of this particular story worth understanding. Now here is where this stops being just a clever lab result and starts being a genuine front in the US-China chip race. The Peking University team did not need cutting-edge lithography to build any of this. Silicon photonics, the technology behind those transceivers and that switch, runs on mature, standard chip fabrication processes, the kind of manufacturing China already has widespread domestic access to, not the bleeding-edge extreme ultraviolet lithography that export controls have specifically targeted for years. Analysts at the Center for Strategic and International Studies have flagged silicon photonics as exactly this, a separate technological path that sidesteps the exact choke point the United States built its entire export control strategy around. You can restrict a country's access to the most advanced transistor fabrication machines in the world. It is a much harder problem to restrict a country's access to glass and light. That distinction is the actual reason this result got attention far beyond a single academic paper. China did not beat Nvidia in a straight fight over raw horsepower. A research team found a path to massive performance gains that does not require winning the transistor arms race at all. And that is a very different, and in some ways more unsettling, kind of breakthrough for anyone whose entire strategy depends on export controls staying effective for another decade. For years, the working assumption inside the US export control strategy has been straightforward. Keep the most advanced lithography machines, the ones only companies like ASML can build, out of Chinese hands, and China's ability to compete at the cutting edge of AI hardware stays capped. That assumption treats the transistor and the machine that etches it as the choke point that matters most. Silicon photonics does not need that choke point at all. It uses fabrication processes that are decades old by chip industry standards, processes China has produced at scale for years without needing a single restricted machine. A strategy built around controlling one narrow gate does not help much if a serious performance gain is walking in through a completely different door. But before this turns into another headline that oversells itself, here is the part almost every recap of this story leaves out. The task these 5 chips were tested on was a distributed image denoising job, cleaning noise out of images using small 5x5 convolution kernels. That is a real computational workload, and it is a legitimate way to benchmark whether an interconnect architecture actually works under load. It is also a narrow, modest one. It is not training a large language model with billions of parameters. It is not running inference on the kind of modern AI system that powers a chatbot or an image generator millions of people use every day. Reporting from the South China Morning Post, cross-checked against VnExpress International's coverage, is clear on this point, even where some of the more excited headlines were not. Scaling from a 5x5 convolution kernel on a denoising task to a full-scale AI model is not a small engineering step. Large models move enormous, constantly shifting blocks of data between thousands of chips at once, not the comparatively tidy, predictable data flow of an image filtering task. The optical switch and the low-loss transceivers solve the physical bottleneck of moving that data quickly and cleanly. They do not, on their own, solve the software and scheduling complexity of coordinating an actual large model training run across that hardware. That gap between a proof of concept and a production-ready system is exactly where most breakthrough headlines quietly die. What would actually close that gap? Independent replication by other labs, first of all, since a single peer-reviewed paper is a strong result, but not yet a validated one across the field. Then, a test on a workload that looks like what data centers actually run today, transformer-based language models instead of convolution kernels, at a scale involving far more than 5 chips talking to each other. And finally, real numbers on cost, an optical switch. This precise is not simple to manufacture at volume, and nothing in the paper claims it is cheap to deploy across a full data center yet. Every one of those steps is a real, multi-year undertaking, not a footnote. And this is not the first time this particular pattern has played out. Over roughly the past year, a string of Chinese optical computing claims have made the rounds, each one touting massive gains over Nvidia hardware in isolated tests. Independent reporting has repeatedly found the same caveat attached to nearly every single one of them. The wins hold up on narrowly scoped lab tasks, chosen specifically because they showcase the architecture's strength. None of them have yet been demonstrated on general large-scale AI workloads, the kind that actually run the world's AI products today, at the scale companies like Nvidia's customers operate at. This result belongs in that same category. Genuinely impressive engineering, tested on a task built to prove the underlying architecture works, not yet proven on the workloads that would actually threaten Nvidia's position inside a real data center. None of that makes the pattern meaningless. A country does not need to win the first round to be worth watching closely. Every one of these narrowly scoped wins is also a working proof that the underlying physics holds up outside a theoretical paper, and each one hands the next research team a validated building block to start from instead of a blank page. The gap between a lab result and a data center is real. It is also the exact gap that closes fastest when a government treats a research direction as a national priority rather than an academic curiosity, which is precisely how China has approached silicon photonics for the past several years. So the honest version of this story is not that China built a faster chip than Nvidia, and it is not nothing either. A team of researchers proved that a machine with roughly 1/9 of a GPU's raw computational power can beat that GPU by a factor of 149 on a real task, simply by refusing to let the chip sit idle, waiting on copper wires to move their data. The bottleneck was never how fast the processors could think. It was always how long they had to wait to get the data that lets them think at all. And that raises the question every chip company banking billions of dollars on the next generation of bigger, hungrier GPUs now has to sit with. If raw processing power was never the deciding factor, then what happens to a strategy built entirely on the assumption that it was? The next choke point might not be the transistor at all. It might be the manufacturing process export controls were built to protect, and China just cleared that exact gap again, with a chip built inside a process, ASML itself, once called impossible.